Hi Amalia. I'm interested in Switzerland lately. Right now, I'm stumbling upon their population on a website. But while looking at all the data and numbers, I wonder, is it possible for us to determine their future population and the past?
Good question. The answer is yes, it is possible.
How?
We can use the multi-gen growth model to analyze the human population growth mathematically. By translating real-world data into equations, we are able to describe the pattern of growth and use it to make reliable predictions.
Oh, that is fascinating. Can you explain it a little bit more?
Sure, I can. Now let's take a closer look at the dataset of the population of Switzerland from the year 2000 to 2020 we have here. This long time span is useful because it allows us to observe how the population changes, that not just over a short period, but across multiple years, making our analysis more reliable. From the data we can clearly observe that the population increases every year. In the year 2000, the population was about 7.18 million. By 2010, it had increased about 7.8 million, and then by 2020, it reached approximately 8.6 million. If we look more closely, we can also notice that the population increases steadily each year with no sudden drops or irregular changes. Because of this smooth and continuous pattern, it suggests that the growth is proportional to current population size. This is exactly the type of behavior that can be modeled using a first-order differential equation. So let's dive in deeper into the calculations and how we obtain the equation.
Okay, now I will explain how we solve this growth problem using differential equation. First, the rate of change of the population proportional to the Switzerland population. So we write the equation as dp over dt equals to kp, where k is a constant. Next, we solve this differential equation using the method of separation of variable. We rearrange the equation by bringing p to one side and t to the other side, giving us 1 over p dp equals to k dt. Then, we integrate both sides. After integrating, we get ln p equals to kt plus c, where c is a constant of integration. To remove the natural logarithm, we convert the equation into exponential form. Then let plus minus e to the power of c equals to a. This gives us p equals ae to the power of kt, where a is constant. After that, we use the initial condition from the data when t equals to 0, which represent the year of 2000, then substitute the population value into the equation. Then we get the value of a. So now our general solution is p equals to 7184250 e to the power of kt. Next, we need to find the value of k. We use another data point, which is the year 2001, where t equals to 1. Substituting the population value into the equation, we solve and get k equals to 0.00632771238018431.
Now we move on to finding the particular solution after we have already determined the value of k. From the general solution of a first-order differential equation for population growth, we have pt equals to ae power of kt. Using the initial condition, which t equals to 0 represents the year 2000, the population is 7184250. So we substitute this into the equation. 7184250 equals to ae power of 0. So now we substitute a back into the equation to form the particular solution. pt equals to 7184250 e power of kt. Next, we use another data point to find the value of k when t equals to 1, which is the year 2001. The population is 7229854. Substituting into the equation, 7229854 equals to 7184250 e power of k. So now we solve for k and we get k equals to 0.0063277. So finally, the particular solution becomes pt equals to 7184250 e power of 0.0063277t. This equation models the population growth over time. Using this model, we can now predict future values such as the population in 2026 by substituting t equals to 26, and also estimate past values by using negative values of t, like t equals to negative 3 for the year 1997. So this shows how differential equation helps us model and predict real-world population growth.
So in this graph, we are comparing the actual population data of Switzerland with our mathematical model. The green points show the real population data from 2000 to 2020, and the red curve represents the particular solution that we obtained from a first-order differential equation. On the x-axis, we have times in years when t equal to 0 is the year 2000, and on the y-axis, we have the population pt. From the graph, we can see that the population is steadily increasing over time. The curve is slightly bent upwards, so this tells us that the growth is not linear. What's important is that the rate curve follows the data points quite closely, which means our model is quite good representation of the actual population. Of course, there are small differences between some points and the curve, but that's normal because real-world data doesn't always follow a perfect pattern. So overall, we can say that the model is quite reliable in showing the general trend of population growth.
To start our analysis, we need to ask, does our mathematical model actually hold up against reality? When we look at the values calculated from our particular solution, the results for the initial years, specifically 2000 and 2001, show a high level of consistency with the actual Swiss population data. The model starts strong. However, as we move into the year 2002 and beyond, a gap begins to emerge. If you look at the trend lines, the actual population of Switzerland begins to climb at a faster rate than our model predicted. While our particular solution suggests a steady path, a real-world data shows more aggressive upward curve. This tells us that while the model was a great starting point, it began to underestimate the growth of the nation for only 2 years.
From the graph as shown here, we can see that the particular solution line is not consistent with the actual value. As such, we decided to calculate the percentage errors in years 2000, 2010 and 2020 to measure the difference between the model and the actual data. From the calculations, the percentage error in year 2000 is 0%. For year 2010, it is 2.19%, and for year 2020, it is 5.61% with an average percentage error of 2.6%.
So, why did the model and reality diverge? The primary reason is that our particular solution assumes a constant exponential growth rate. In mathematics, that looks like a smooth curve, but in the real world, population growth is messy.
Switzerland population isn't just a math equation, it's driven by population birth and death rates, and perhaps most importantly, migration patterns and government policies. These variables can change overnight due to economic shifts or global events.
Furthermore, we have to consider technicalities. Small rounding differences in our growth constant or initial data can compound over time, leading to those slight increases we see annually.
In short, while our model captures the essence of growth, the complexities of human life and policy ensure that reality will always be a tiny bit more dynamic than a fixed equation.
So, as a conclusion, we can see that the particular solution we obtained is able to model the population growth of Switzerland quite well over the given time period. The graph shows that the model follows the general trend of the actual data, although there are slight differences between the calculated values and the real data point. These differences may be caused by real-world factors that are not included in the model, such as migration, changes in birth and death rates, economic conditions, or government policies. Since our model assumes a constant growth rate, it cannot fully capture these variations. Overall, the particular solution is still useful as it gives a good approximation and helps us to understand how population changes over time using differential equations.